determine the diameter of the electrode and PCD. 뒤에 거는 칠판도 쓰니까.
I show you the difference between EAF and SAF. In EAF, the objective is to concentrate in the center. EAF, the objective is to have a concentrated heat source. Because the free arc is the source, and it is anyway it is radiating. So radiating means that of course when you begin you have the scrap. It is very good because scrap is around the arcs and scrap takes all the heat. But when we have no more scrap, we have only some slack. Then it is good to have. It is good that the arcs are in the center, so that they don't radiate too much on the panels, on the walls. It's good to have the maximum distance. Okay. In case of SAF, is quite different. In case of SAF, You have small arcs. And the heat of the small arcs, the heat from the small arcs is all transmitted to the slag because there is no free space. The arcs will not radiate on the walls. There is no risk. But the second mode of transfer is resistance heating between the and this one is organized like this. These are the current lines. So the current lines must best cover the surface, because the current line will heat the slag. Also the arcs, but the arc heat will be catched by slag, no problem. But the current lines must be well distributed over all bath surface. And when you calculate the current lines, and this is true, is the current lines, the lines do not depend on the current figure. The current lines, are the same for 90 kiloamps or 60 kiloamps, or you understand? The lines.
Yeah.
Of course, the intensity of each line will be more or less, but the current lines, because the resistance of the charge is the same, the current lines will be the same. So, disregarding current figure. So this you can calculate, assuming resistance of the slag. Many people have calculated this, and the result of this is that the pitch circle, meaning this circle, must be around between 0.4 and 0.40 and 0.5. I take 0.45. There are discussions. People say it's better to take it larger to have no frozen region. Because here we have a bit frozen region. But roughly. So it's not a fixed constant, but some people take this 0.5.
This pi means pitch circle. Pitch circle diameter.
Pitch. This is pitch circle diameter. Is
How to
0.45
calculate?
times the diameter of the SAF.
This 0.5 times pi. Pi meaning pi SF means all.
No, this is for me. This is diameter. If you want, I put it like this. Diameter. If you prefer. Okay.
The diameter of SAF means the inside diameter.
Inside the walls, yes. Diameter of SAF mass, actually. This.
Is there any limitation for the distance between electrode and mass wall?
No, because you see, in this case, there is no direct transfer to the wall. The situation is much different.
In case of EAF, we consider about the arc index or refractory index.
Yes, the radiation index is the key. Yes. Here you don't have this.
But in case of SAF, we don't need to have that.
In case of SAF, you must position the electrodes so that the current lines best cover the bath.
This 0.5 we can, how we can calculation? Do you have any formula?
This is the formula. because the dimension of this one is dimensioning of the SAF, what we did. So the diameter we already know from dimensioning. Globally, the SAF surface, the surface gives the diameter.
And how about the distance between electrodes? Is there some recommendation for
Because this is
between
the pitch circle is the circle of the center of the electrode. So once you have defined the pitch circle, the electrode have a position, because this is, of course, this is you understand, this is 120 degrees each.
I can calculate the distance between electrodes.
The distance between electrode, there you need the diameter of the electrode, and that's the second formula. Diameter of electrode.
And is there any recommended distance between electrodes?
No. The recommendation, this is the result, because if you know the pitch circle and you know the diameter of electrode, the distance is forced. Huh? You agree?
No.
So the diameter of the electrode is just corresponding, can be defined when you know the max current. And the criteria is that the current density should be less than about 4 or 5 ampere per square centimeter.
It is.
You know, for the electrodes of the EAF, current density. This is graphite. Is about 40 amps per square centimeter. And here it's 10 times less. Here I take also like this, I take the middle, the average 4.5.
In case of graphite electrode, the current density is different depending on the diameter.
No, it's the current density is the definition is the current divided by surface.
Yeah.
But of course, graphite electrodes, which are baked at 2000 more than 2000 degrees, they withstand much higher current densities than these self-baking electrodes.
In our case, in Gwangyang Bio plant, we can use the graphite electrode. In this case, we choose the.
You can use this, yes, because
Korea?
for a small furnace, it's better to use graphite electrodes, because unless your electrodes are too big for the small furnace.
그러면 우리도 40A 기준으로 해야 되겠네요.
We can make an example here, huh? for example, high meter.
얘네들이 했잖아. 130에서 200인데 40A 이하로.
그렇죠. 저조건.
무조건 되는 거지, 그지?
그렇죠. 근데 이제 이걸 하려면 이거를 힘줄 수 있는 이제 부스가 하나. 그게 밀도가 이제 그걸 이만큼 맞춰줄 수 있는 이만큼 맞추면 이제 커져야 돼요. 밀도가 커져야 되니까 부스가 커지든가 아움이 커지든가.
근데 어차피 일렉트로드 자체가 지금 작기 때문에 이만큼 안 나오더라고. 그지?
그만큼은 안 나오고 한
어느 정도 우리가 선생님 일렉트로드 넣는 것도
한 20에서 한 25 정도 약간 40까지는 나올게. 보면은 그게 지금 130이면
Shall we make an example? I will tell you. Their maximum current is 90 kiloamps. Okay? I don't remember the diameter. We calculate what I recommend. So, the electron, what do you say, section, the surface section is 90, see, 90,000 times 4.5, and these are square centimeters. You agree? I just use this, huh?
Yeah.
Huh? Can you calculate?
서비스는 좀 나눠져 곱하면 나눠져야지 면적으로 나눠져
면적으로
90화 나누기 뭐 이건 센티미터당 암페어니까 이건 나눠져야 면적이 나눠져 isn't it? Like the
면적이
Let me see.
곱하면은
No, it's not.
암페어니까
No, it's not that. No.
divide
The criteria is 4.5 ampere per square centimeter. So it's
divide
so it's this is the current divided by surface.
네.
And now we have the current, and we want the surface. The surface is the current over. Excuse me. And this is simple then, because it is about 2,000.
20,000
And so the electrode diameter is we divide by P.
About 160
Centimeter.
centimeter.
Okay. And what is the real diameter of the electrode in diameter? I think it's 1.6 meters, which is about the same. Example 1, example 2. Large manganese SAF, 15 meters diameter, and working with 130 kilograms. So here we have S is about 30,000.
It's about 30,000.
30,000? And the diameter?
Exactly, it's about 29,000.
29?
Yeah, 29.
And the diameter? far from 2 meters.
192.
Okay. And the real diameter they have is 1.9. You see, it must be like this.
First diameter is 160. 0.5.
No, I tell you, I made the calculation before, but this is what all people take. Okay, some take, some say 5 and some 4. It's like here, you know. This is not it's not a international law. Huh? Some people say I limit to 30. Yeah?
Well, we have to check the electrode graphite electrode company maker. They select some color density per each electrode size.
It depends from the quality of
that's
the quality
right.
of graphite.
Made in China and made in Japan is different.
Exactly.
지금 그 우리 일렉트로드 보면 저기 나와 있거든. color density. 근데 이제 이쪽 SAF 같은 경우는 쿠킹을 해야 되잖아요. 이제 그게 이제 그 따라서 우리가 달라지는 거예요. 이제 기술이 되게 중요한 거지. When we design the SAF, the cooking is cooking of the electrode shall be done at site.
Yes,
So,
self-baking.
Yeah,
Of
it is one of the important technology. Yeah, the how to cook and how make a density.
It's not
yeah.
how to cook. It's the mixture.
Yeah, mixtures.
That is-
yeah,
that
this
is-
is important.
That is the. It's like in your kitchen. Huh?
Yeah, yeah.
The quality of your meal is is the quality of your products.
Yeah. And when
Okay, then the cook may be important, but in that case, the cook is you cannot change the cook. It's always the same. It's the furnace itself. It takes some heat from the furnace.
So
So-
I worry that when we calculate the color density of the SAF electrode and we assume the 4.5, but the cooking is not good and the color density is lower.
You are, yes,
or-
yes,
It is, I think.
yes. But for the design, you must take this because the rest is operation. Huh? The rest is proper operation. You cannot say I will make it bigger to compensate bad operation.
그러면 뭐 이것도 다 알고 있는 계산 방법이잖아.
알고 있는데 일단 PCD는 그 이너 다이아의 0.4
왜 그래야 되지? 그게 좀
저게 공식이에요.
뭐 저는 여러 사람들이 경험적으로 이제 계산한 결과가죠. 여기는 이제 아크 인덱스전 저런 인덱스가 있는 건 없고 그런 개념은
그게 있으니까. 나도 저걸 밝혀봐야 되니까.
왜 적은지.
Do you have some paper, technical paper for how to decide what make the 0.45?
Yes. For this,
Yeah.
you maybe I find something. The base I explain. The base is the calculation of the current line,
Yeah.
and then you see that the current lines they must cover the.
Yeah, that's right.
And this is not depending on the current itself, because if the current is 100 kiloamps or 50 kiloamps, the current lines are the same. The line intensity is different, but the lines behave the same. And so the base must be this. I think I have seen this publication. a long time ago. I don't have
So
it.
if next year when we do our technology, at that time the electrician or mechanical can maybe lose it.
Yes, maybe he knows. Yes.
그럼 나중에 내년 과제할 때 전기기계 담당 인원이 오면 그때 활용해 보면 되겠지. SF 관련 뭐 책들이 어떤 게 있는지 사실 좀 찾아보고 해야 될 것 같고. 나한테 그 성과는 있었던 것 같은데, SF. 직접 말하면. 내가 충분하고 다르고.
Okay. So we move to the ferronickel mass energy balance. And using the same Excel sheet. And okay, actually what I did is I made first the calculation and then I put a recommended mix. I just mean that the coke consumption is actually about what I calculated here using the formula. Okay. I showed you on one slide in my presentation that in case of ferronickel, you may have the ore is always poor in nickel, but nevertheless you may have differences, and you may have you remember maybe the slag composition can be very different due to different ore types, and so this is an example taken from one column of the slide, of the PowerPoint slide, and the details of the origin of this data are in one publication you have in the documentation list. So, but I think I sent you the article because I had the article. I sent you a scan of the article. Okay? It's the article with the word processing laterite, or I think the word laterite or laterites. But laterite is the word for this form, for the rock, including nickel.
Laterite.
Laterite.
L-A-T-E-R-I-T-E.
I write it larger. Laterite. And this article you have. So actually the laterite ores include, of course, a little bit nickel. That is the objective, but the most they include is silica and magnesium. And the different origins, then the proportion of the two vary a little bit. So here you can see in the data, in the analysis, we have 47% silica in the ore. We have 28% magnesia. And of course we have iron. We have Fe. And here I must say something. Actually, of course, the ore contains Fe2O3 and not FeO. But since before the SAF, you have a kiln with preheating and with using coal. As for MnO2, at low temperature, this is reduced to FeO. And therefore, in this analysis, which is the analysis entering the SAF, the iron is under the form of FeO. You understand?
In most cases, the ore is from kiln. In
Yes,
case of
yes.
nickel.
Yes, you will see in the publication, in all cases, practically. Because the reason is that in this case, look, you have 2 to 3% nickel, of sometimes less than 2%. So here, these two together is 75, 80%. And this is what we call gang. You know the word gang? Gang is ganga. And at the contrary of the manganese ore, here you have 80% gang. And when you have so much gang, you'd better preheat. You'd better have the gang preheated. And using not electricity, using coal. And that's the purpose. Therefore, but of course, if once you have a customer having no kiln, you will enter according the analysis according. You will enter Fe2O3. You will enter the analysis he gives you, of course.
The rotary kiln's main purpose is the reduction of the ferro
No,
Fe and the heating of
Yes, both. Is the preheating
Yeah.
to 800 degree,
Mhm.
but when you preheat Fe2O3 to 800 degree, you will reduce it to FeO with coal, with of
With
course,
core, yeah.
with a reducer. So I explained to you in the kiln, coal is giving the volatiles, which are the fuel,
Yeah.
which are burnt with air, and the carbon fix is a little bit, it's beginning the pre-reduction work. It may be also, yes, of course, it may be also that you this we cannot say, that you reduce some nickel. But if you see in the calculation the importance of that, it can be, you see, nickel is very low. So if nickel is partially pre-reduced, actually I don't know, it may be, because nickel is also easy, rather easy to reduce. But here we make the assumption that we have still nickel oxide. And actually, you see, here the sum is 100. But the sum is 100 because I have arranged it like this. Because if you take the figures of the publication, the sum is not 100. That means that there are some components, not some small components, not given. And then what I did, I adjusted it. You understand? I proportionally increased each one to have 100. If you are sure that these are the main components, this is okay doing that. But of course, the best is always to have a complete analysis balanced to 100%. Okay, so having this ore with high silica magnesia, it's the same. Silica is here, has a very low reduction yield. Very low. And then you have magnesia is not reduced at all, of course. This is here. Magnesia not reduced at all. Silica very, very few. And in case of the iron, you remember I explained in the mass balance that iron you reduce in order to have a correct proportion of iron to nickel. Meaning, in this case, and the rest you do not reduce, the rest iron will be rejected in slag. In this case, you have very few nickel. The first objective is to fully reduce the nickel. And then for the iron, if the proportion of iron to nickel is correct in the ore, you don't need, you can reduce all the iron. But if you have too much iron in proportion, because it's a poor ore, then you will charge less carbon, and so you put some iron, you will leave some iron in form of FeO in the slag. But nickel will be practically fully reduced. But of course, it is nevertheless the question that when giving more iron to the slag, you will lose a little bit nickel. You remember? Because nickel in the slag we want to be very low, 0.07 or so in slag. While iron can be 10, 20. In one case, I have seen 30%, but 10 to 20% is normal. Okay, then you see the mass balance is saying that for 100 kilo ore, we obtain 0.1 kilo Fe in the metal. We obtain in the metal 7.7 kilo iron, and we obtain 2.3 kilo nickel. And the carbon we target at 2%. The carbon, this is the assumption, 2%. And then the calculation proceeds, and it shows that for 100 kilo input, you have 10.3 kilo metal. And this gives you 22.3% nickel, 75% iron, and 0.6% silicon, and 2% carbon.
지금 시트는 우리 망간에 그냥 이렇게 지금 똑같은 게 이제 가는 거 같죠?
그렇죠. 똑같아.
그래서 이걸 바꿨었는데 수십 안 바꿔 됩니다.
이제
FeO
쪽에 바꿨습니다.
여기를
Yesterday, when we considered the ferromangan calculation, we changed the calculation for FeO in slag.
No, we had FeO in slag.
Yeah. Last time we changed the formula for FeO.
The formula.
Yeah.
Yes, but here it should be okay. It should be okay because you see we have it should be okay. Yes, you're right. This was corrected. Yes,
This is corrected.
let's check. Yes, it's correct.
Right.
And you see we have 13% FeO. This is surprising to me because this proportion. Yes, okay. No, the proportion. No, it's okay. No, I was confusing. It's not the iron. It's FeO.
FeO.
Yeah, FeO. That's correct. And you see, okay, here we have 0.1% NEO. Okay, this is already a bit high. People, but I mean, you know, I explained to you that, of course, people are concentrated on recovery, the best recovery of nickel. But here, if you obtain in the calculation 0.10 or 0.07, for the results, it's changing nothing for the energy and for the mass balance. It's just that you could say it can be improved and maybe, but okay. Where is nickel? Let's put 98 instead of 97. We have it. You understand? What I changed? I changed the yield of nickel reduction. So when people work properly, they have this. But you see, it did not change anything here. You understand? Because the amount is 0.06 compared to 88. It's nothing now. Before it was 0.09.
I mean the amount is very small and
Yeah.
the difference is very little, just a little.
You have questions? In principle, it's exactly the same than for manganese ore. Except for manganese ore, you remember the difficulty then that okay, we have two ore types, and two manganese oxides.
그 FeO 그건 어떻게 이해됐어?
네?
FeO 얘기하는 거는 이거는 안 바꿀 때는 그 앞에도 만감 바꿨잖아.
예.
아 이게 지금 FeO만 들어오지. 그러니까 안 바꿔야 된다는
예.
거예요?
이건 FeO만 고려하는 거고.
그럼 이거 식을 다른 걸 쓰고 써야 된다는 얘기잖아.
니켈하고 망간하고 시트를
하나를 같이 쓸 수 있어야 되는데.
혹시 쓰려면
어제 망간 거는 FeO로 밑에서 변하기 때문에 넣어준 거지.
네.
그쵸, 생각이 필요 있을 것 같은데. FeO3 같은 경우는 FeO를 바꿔주는 거고.
근데 똑같이 얘도 니켈도 그 킬런 안 하고 할 수도 있잖아. 그러면 어차피 같은 식을 써야 되는 거 아닌 것 같은데.
그러니까.
킬런 안 하면은 똑같잖아, 망간이랑.
We discussed when we calculate the ferromangan and ferronickel, we have to use a different Excel sheet, right?
No, it's we could use the same, of course.
But,
It's everything is same.
but in case of the FEO in slag,
No. But this is only what the key assumption. What may be different
yeah, that's right.
is here the yield of reduction, and this is more or less experience.
No, I mean that is okay. Yield reduction yield is okay because it is needed some experience.
Yes.
But I mean the in slag FEO calculation, in
No.
case of the
No,
ferromangan,
it's-
G.
Ah,
no,
that's-
metal. Yeah.
No. I think here I have. You mean this?
Yeah.
This one.
That one.
This is FEO in slag. And-
W22 cell.
It is.
No. Slag. Sorry.
FEO in slag. It is.
Yeah, FEO slag.
It says that it is eventually the remaining Fe2O3. You see
Zero.
this one,
Mhm.
let's put it. You see this one, but the remaining Fe2O3 is 0.
Yeah. Because of the rotary kilns, yeah?
Yes, but no, but even here, even if there is some, it is 100 here, and 100 minus 100 is 0.
No. I mean, I understand what you say, yeah. But I mean, the last day we changed the equation
Yes,
because of
yes.
ferromangas from Fe2O3 to change the FeO in SAF.
Yes.
But in case of FeO, most of the FeO shall be reduced in the rotary kiln. So
Yes.
and you consider
Yes.
just FeO. But then ferronickel's equations in same cell and ferromangan's equation in same cell is different. Both is different.
No, I think it should not be different. Let's check. Okay?
Yeah, in case of ferromangan, you write down
Yes, I changed
change
it.
the
The
FeO
reason,
to FeO. Yeah.
Yes. The reason is that for ferromangan, I changed something here. I don't remember exactly. It was changed afterwards. It was not done together. But I explained here that this formula is true in any case, because in any case, if you have Fe2O3, even if you don't have a kiln, you have something here. But if you have reduction yield of 100, you see the first term is 0. You understand? Even if you have Fe2O3 and you have 100, Fe2O3 will always be fully reduced.
Look, I mean, when we used your Excel,
The same sheet, you mean?
yeah, same sheet. But
Okay.
basically-
You know what? I will check this
Yeah.
separately. I will check this, and I give you the updated. Huh? I send you the updated, which is convenient for both.
Mhm.
But I checked this separately, so I am sure. Okay, with the same method, we calculate the amount of oxygen which is removed due to the reduction yields. Remember, so it's a huge formula, but it's just saying in each line I multiply the total amount of oxygen by the proportion, by the yield, by the reduction yield.
Would you explain again about the Q? It's not Q19 or Q. The reason that it is this.
Q19. Yes, this is this one.
MNO2.
Yes. Yes.
MNO2에서
Q90. So we have the here we have 0, of course.
Yes.
But anyway, if it is not 0, you take this number
in case of Q12.
Yes,
No.
okay. No, it is the reason is because you add 2 reduction yields.
Okay.
You see, here we have because we have MNO2. It is completely reduced to MNO, and after it is partly reduced to MN. This is completely meaning 100%, and this is 71%. Okay. So the oxygen here, this proportion of oxygen, this is this number, okay? Okay?
Yes.
And when you fully reduce it to MNO, actually it is not the reduction yield of 100% is not fully eliminating oxygen. It's only half of oxygen removed. You understand?
Yes. When the MNO2 without
Yes.
it to MNO, or
Yes.
only the half of oxygen.
Half of oxygen, not 100% of oxygen.
Yeah.
The MNO2 is 100% reduced to MNO,
Yeah.
but oxygen is only half
Half.
removed. You understand?
Yeah.
Because FPO, FP2O3, FPO,
And it's similar for FEO, but Fe2O3 and FEO.
so formula is different.
Yes, okay, I will check to have a... But, okay, formula is different, but result is correct in both cases.
So you use the Q19/2 because the only half of oxygen reducted in this process.
Yes. And after you say here, it's